Okay, so welcome back to our video. So here we have both a integral containing where the integrand contains both inverse trigonometric function and a trigonometric function. And we have that the integral from 0 to pi of the arctangent of y to the power cosine of x dx, where the parameter for y is greater than or equal to 0. Interestingly, this integral is nice because with this given parameter, no matter what of y you choose within this condition, the areas are, rather the integral value or the area, however you want to interpret, is actually going to be the same. Now you might be thinking, what is the answer to this integral? Then that's what we're going to calculate. So if you're wondering what happens if it's less than 0, then it's the whole integral is actually just going to be undefined. It's if you actually graph this out and take a look at things into geometrically, you can see that the graph of our integrand is actually symmetric because it's also an even function, so it would make sense to interpret it in that situation. Say if you were, for example, that if this was instead sine of x, so we replace this with sine of x, hence that being an odd function, then it won't act as the same for the finite value of the area we're trying to calculate. So that's where things gets a little bit different. But hence for this situation over here, this is actually nice. So in turn, so to calculate this, it's actually just usually involving with some U substitutions and some identities involving, the arctangent, which I did prove in one of my previous videos. I actually used this identity so many times, I can link that in the description again. But it's also worth noting that I realized that the proof that I did for that arctangent identity is only for the case of x is greater than 0, strictly. And not with the negative case. If there was a time that if I were to cover the negative case, hopefully that would be awesome. But just letting you know ahead of time that the arctangent case for the identity we'll be using is for greater than 0, which is actually applicable in the situation we'll be working with. So anyways, nothing more than that, so let's jump right in. So let's start with the U substitution and say that if we let U equals cosine of x, so we want to be careful here because if we were to differentiate just the way it is, so how will we actually figure out a replacement for dx? Don't fret, we can actually just take the inverse cosine of both sides. So that means this will be x is equal to inverse cosine of u. Then we can actually differentiate both sides and have that dx is equal to -1 divided by the square root of 1 minus u squared and then du. And so in turn, we can actually now rewrite this new expression with our new bounds. So if we were to plug in pi for x, then that would have to mean that we're going to get a -1 on the top. And if we plug in 0, so we'll get a 1 on the bottom. And then if we actually just plug this all in back in substitution, so this should be the negative. So negative arctan of y to the power u, and then divided by the square root of 1 minus u squared and then du, then some things can change. So for one thing, we have to flip the bounds and then that'll turn into negative, but then that negatives will cancel. And so we're now dealing with just positive. So we can write this as 1 and -1 over here. And then everything is just the same integrand except excluding the negative sign. So y to the power u and then divided by the square root of 1 minus u squared and then du. Here's a little trick that we're going to be doing so we can actually deal with that arctangent identity as mentioned. What we can do, and this is more about taking this into another creative approach, and there's another way you can do this, you can, but this is the method that I think is a little easier to work around with. We're going to split this interval up. So we're actually going to write this as first start off with from -1 to 0 of our integrand given, and then we're going to do the same thing going on rest forward. So the first part is from -1 to 0, and then we're going to add this from the remaining interval from 0 to 1 of the same integrand listed just above me. So we're going to take a little focus on just this integral itself. So I think you can see where I'm going with this. We're going to have to do another U substitution. I'll call this a different variable though, since U has already been used. So we're going to let this, we'll let you use U again. In turn, we have that U is going to equal -W. And so if we differentiate both sides, so I have du is equal to -dw. Let me just put this over here so we're dealing with what integral. Not only that, we have to fix our bounds. So let's see. If I plug in 0 for u, then that means w will be 0. If I plug in -1, then that would have to mean w would have to be +1. And then so we have arctan of y to the power w, or negative w, excuse me. And then all this being divided by, so if I just plug in the square root of 1 minus and then the input negative w square, easily enough that just come back to positive, and then that'd be negative w over here. And so now in turn 4, we can actually do a little bit of some changes. For one, we can flip the bounds again, and so that'll be a negative. Then that negative will cancel out. And another thing, as I mentioned, that negative w squared is always going to be positive. So it's just back to the same thing. Since again, the square root of 1 minus u squared is always going to be an even function. So this is 1 over here, 0, and then arctan of y to the negative w, then divided by the square root of 1 minus w squared, and then dw. And so interestingly, we see that this integral matches with this integral, and it wouldn't matter what variable you're using since it's just a place of a dummy variable. If you integrate it, you're going to get the same value for over here. So this means that we can actually replace this integral with this new integral over here. And this is nice because it's actually integrating under the same interval. So there's some properties we can be using, not the word might, we will be. Such specifically, we can actually use linearity. So let me actually first go back to the original integral. Well, specifically this one first that we started with the substitution. So we have negative 1 to 1 of, arctan of y to the power u divided by the square root of 1 minus u squared, then du. Then we see that I replace this integral with this integral over here, and we have 0 to 1 of arctan of y to the negative u, again, dummy variable, so we can put this back into the world of u, and then divided by the square root of 1 minus u squared, du, and then add this back with this integral, or this integral over here. So integral from 0 to 1 of arctan of y to the power positive u, and then divided by the square root of 1 minus u squared, then du. And so from here, again, as mentioned, I can actually use linearity. It's under symmetric intervals, well, the same intervals. So this means in turn, so now I have that this is the integral from 0 to 1 of, let's see, first I'll write this as 1 divided by the square root of 1 minus u squared. And then now we can multiply this by arctan of y to the power negative u, and then add this with arctan of y to the power positive u, and then du. And so here is the identity we will be using, the arctangent identity. And that says that specifically we're dealing with the case for u is greater than 0, which is perfect in this situation, in this interval we're dealing with. Then we have that arctan of y to the power u, add this with arctan of, actually, I said that wrong. Let me actually first state the identity itself, and then we can actually plug it in. So arctan of u, and then plus arctan of 1 divided by u, this is going to equal pi over 2. And that's for the case of u is greater than 0. So if you want to check out that proof I did, I'll link that in the description below. It's actually from a different integral that I did of dealing with the golden ratio. So with this identity, now we can actually just plug this input back in. And so that would have to mean that arctan of y to the power u, add this with arctan of 1 divided by y to the power u. This is the same thing as just y to the negative u, so that's fine. This is going to equal pi divided by 2. And so we're actually just about almost done. So if I actually just put this back into the integral, so 0, 1, 1 divided by the square root of 1 minus u squared, then plug this back in for this identity that she said that's pi divided by 2, du. Then interestingly, this is, we can just factor out the pi over 2 and then 1 over the square root of 1 minus u squared. That's easy antiderivative of fine, and say that that's actually just arc sine, so inverse sine of u, and we evaluate this from 0 to 1. And so in turn, that would have to mean that pi over 2, we know that arc sine of 1 is just pi over 2, and then we know that arc sine of 0 is just 0. And so therefore the final answer for no matter what y we choose greater than or equal to 0 is going to equal pi squared divided by 4. And just like that, we are done. We have found our value of no matter what, as I just said, no matter what y value, what positive real numbers y, or including 0 as well, that we choose from to plug in back to this integral, then we always get this. And as mentioned, anything less than y, so the negatives, this whole entire integral is always going to be undefined. So yeah, that's pretty cool if you ask me.